Video, we're going to continue our discussion of memory management in the XV6 teaching operating system. So in this video, we're turning our attention to the creation of the process address space. So the address space that's created for a process and that's meant to perform isolation for a user process. So yeah, we'll continue looking at the vm.c file. We'll look at the UVM functions for creating user address space process tables, and probably we'll spend most of our time looking at the exec system call and how actually a new address space is created and we load an image from a file into it and start executing it. All right, so if you're ready, let's go ahead and get started then. Okay, so as we've mentioned before, each process in an operating system usually has its own page table, and that's the way XV6 does it. So when XV6 switches between processes, it also changes the page table, right? So it has to keep track of where the page table is for each process, and whenever it's doing a process switch, it has to change that particular special register once it's ready to let the new process start running to change the virtual address space for the translation from the process address space to actual physical memory. So here's kind of a layout of what a process address space will look like. So in the virtual address space or the process address space, addresses start at 0. It appears as one contiguous address space, right? So every address in the address space can be accessed from 0, 1, 2 up to the max virtual address that we have in there. So that's got what we mean by contiguous. The process's address space has pages with text. In this context, when we're talking about like binaries or ELF headers, this refers to pages in an image that contain executable code. So text sections will be loaded with read and execute instructions. Also, most all these pages that are accessible in the process address space will have the U set for the process table entry, meaning that it's executable by user code. So if this isn't set, then it's not going to be viewable or executable when we're in user mode, right? And if I forgot to mention this before, these settings, these flags in the page table entries, when you set these, this also happens at the hardware level. So if you're doing an instruction that's trying to write onto a page, and you've just done a translation, and the page table entry didn't have write permissions, that will cause a trap to happen. So the write won't actually happen. You'll actually get an error. Or if you're currently in user mode and you try and read or write something, and the page table entry where you're trying to read or write to doesn't have the U permission set, again, you'll get a trap, and this happens at the hardware level. So another thing, so data then, above the code in the virtual address space is normally where the data will be loaded. So pre-initialized data, constants, global variables. So since this can contain variables, I guess typically this will be both read and write, but it won't be executable. So we don't want to have the execute set here. So we don't accidentally jump and try to start fetching and execute code in a data section like this. So then above the code and the data that's part of the image, a stack will be created. In XV6, just a single page is used for user stacks, the same for the kernel stack, so it's rather limited in size. And a guard page. So stacks actually grow towards smaller addresses. We'll see that when we look at the details of the code here that sets up and puts the arguments onto the initial stack when we create a new process here. So that means that the stack pointer will initially be at the highest address, and every time you're pushing data on the stack, it's actually decreasing the top of the stack pointer. So it's going down towards lower addresses. And if you pop a stack frame off or pop things off of the function stack, it will actually increase the stack pointer. And like we talked about before, when it's actually creating the stack, it's going to create 2 pages, and the page lower in memory will actually be a guard page, so it will set this so it's not valid. So it'll unset the PTE_V valid bit for the page table entry, so that if any read or write is trying to be done on the guard page, again, you'll get a trap that will happen in the hardware. Above that will be the heap, and then again, we'll talk more about these in later lectures, but then trap frames and trap frame and trampoline page are mapped to the top of memory, and these don't have the U set, so we can't actually execute these instructions in the trampoline page if we're in user mode. We have to be in kernel mode before we can do those things. So these initial contents of the stack are actually created by the exec system call. So we'll see this. So remember, if you remember when we looked at the exec system call using it, you had to pass in an argv, so an array of argument values and an argument count. So those things you pass into the exec actually get pre-populated onto the initial process stack in this order. So it actually puts the command line argument 0, and then 1, 2, 3 down to the command line argument in. So it puts in that order, and for reasons, I don't know exactly the reasons, but you'll see how it does this, that the actual pointers, the actual addresses of these arguments are then on the stack in the reverse order. So after we actually have the command line argument values, the strings, and these are all null terminated strings, then you'll have the address for the last argument in, the address for the argument in -1, down to the address for argument 0 will be basically at the top of the stack. So remember, the stack is growing this way. So this is the bottom of the stack down to the top of the stack. So you have the very last thing on the initial stack is the actual argv itself, the address of argument 0. Right? So this would be pointing to the same kind of thing you get in argv in main when you write a user program. So a few more words about the properties of xv6's use of the page tables here, if we didn't cover all these yet. So each process's page table translates the same virtual address space to different pages of physical memory, obviously. So there are special ways in some operating systems to share some memory, but the default is all the memory is going to be allocated and only mapped in one process's virtual address space. Okay? So each process has its own private memory that can't be seen or manipulated or overwritten by other processes running on the system. So I already mentioned that each process virtual address space sees it as having a contiguous address space starting at 0 going up to max VA. And max VA is that since we use 38 bits for a virtual address, it's 2 to the power 38 is the maximum virtual address that we can have in xv6's virtual address space. But these mappings, so we're not showing the mappings to actual physical addresses. So these are going to be mapped to lots of non-contiguous pages. So the pages that are allocated for each process are not going to be all together in actual physical memory. They just appear to be all contiguous from 0 up in the address space, the virtual address space of the process, basically. And again, we keep mentioning the trampoline and trap frame. We'll see specifics of those later, but those are mapped at the top of the user address space, like they were for the kernel address space that we talked about, without the user flag, user bit set in the process table entry, in the page table entry, which again means that if you're in user mode and you try and execute code without that set, trap will happen, so an error will happen, and won't actually perform the operation. So back to the exec system call, the kexec. So we start by just opening up the file that's given in the path name here. So I won't go into why we're not using like open, close, and read. We're using some lower level things here, but the effect is the same. So we're really kind of opening the file here and reading it in from this inode pointer that gets returned from here. So basically anything that has particular values as the first couple of things in the elf header here. Again. So here the first couple of bytes are these. So every elf file just writes these bytes as the first couple of bytes into the file here. So if those are written there, it's assumed, at least by XV6, that this is a valid ELF, and it goes in and tries to read it in. So basically, each one of those sections, there's going to be multiple sections, some text, some data. So text actually is what holds code, some that holds data. Let's show an example of a ELF header like the textbook did. So the object dump command line tool knows you can give different flags to get more information out of this, but it knows the basics of an ELF formatted binary file like this. So, for example, the _init is the actual compiled version of the init process. So it's the same thing the textbook shows. So there's kind of like 4 sections in here. So 4 program headers. So there's ELF headers, and then the program sections are called program headers in the code here. I won't discuss kind of this one or the one labeled stack here, but like the textbook discusses, like the first one here is offset 1000 in the file. So that's where the start of this is. I think this first one corresponds to just the ELF header itself. And so then after that we have this program header, which is actually a text header, a code header. So I can kind of tell that because its permissions are read, execute. So these are the things. Let's bring this up. When we read in one of these program headers, like these flags are what get read into here. So this is read, execute, and that's the offset in the file. But this is the offset of where we should load this into the virtual address space. So it actually should be loaded at address 0, because this contains the code, including the code for the main function where we're going to actually start. And if I remember right, the entry up in the ELF header is the actual virtual address of the first instruction in one of these program headers that the program counter needs to be set to when we start fetch executing from when we're running a user process. So, and then there's another one. This is probably the data segment. So I can mostly tell this, so this is supposed to be loaded to virtual address starting at 1000 instead of at 0. And it's offset in the file at address 2000. Hexadecimal 2000 in the file. But, again, we can tell from the flags that it's read write, so this is data. So global constants and global variables, especially global variables that need to be writable, are probably in this program header. So this file has, like I said, I think that this is just the ELF header information is this first one. Then we've got one program header that has the code, one that has the data, and then this has something to do with creating the stack, although I have to go back and look because it shows a virtual address of 0. And as we'll see, the exec actually creates the stack itself, so I'm not certain how this is used here. But anyway, so that's what this loop is basically doing. If you don't quite get it, we've loaded in this ELF file, and this is going to go through each of the program section headers, which is shortened as PH here, right? So each time through the loop, we'll have a different one of the program segment headers in order to load the code or the data from that segment in the file into memory. So I skipped over it, but basically, remember, exec is creating, fork creates a new process. So fork is the thing that actually creates a new process in the process table, but exec actually loads new code. So this is where a new page table is created. So we briefly mentioned it before. When we do the fork, it does have its own page table, but it just makes a copy of all the code and copies over all the code into a corresponding page table after the initial fork, right? So if you don't do an exec, you'll have 2 processes running, but they'll be executing the same code. It'll be copies of the code, and they'll actually have their own page tables, but the code will be the same. So here, in order if we want to execute different code, we have to call the exec. Remember. So to do that, I mean, we're going to actually want a new page table. So this is what actually creates a new page table. This is in this is in process.c, so it's not in VM. So this creates a user page table and sets up the basics. So it's basically empty when it creates this, just setting up the trampoline and the trap page. But it does use map pages that we saw before. It also uses the UVM function. So here is where we get the first one, where it's calling the user virtual memory create. So this will be similar to the KVM make, but this is allocating a new page table and initializing it. So yeah, this actually UVM create will just create the initial root page table in the 3 level structure there, and initialize everything to 0, and just return that, the root of the new page table that we're going to start setting up and creating by loading in this new image. So before I move on, I'll just point out, so this is the new page table that's being set up and created, and I believe at this point we only have the root of the 3-level page table structure. If you look back at, sorry, not back to kexec. So back in kexec, we're creating this new process page table. If you look here, if everything goes well, at the very end here, when we think we're ready to commit to the new page table, an image that's loaded, and start running from it, we remember the old page table. We set the new page table for the process entry in the process table, and so on. So I'll come back to that, but I just wanted to point out that we're creating this new page table. We still have the old page table. That can't be kind of released until the very end here, when we're sure that we've successfully loaded in a new image and can start executing from it. So going back up here to where we're loading the different, sorry, I want to open back up my elf.header file. So here we're going to start loading the different sections in from the file here. So that's what this loop does. Okay? So, I mean, just again, very basically, we start at section 0. So the elf header, the very first thing we read in up here, has the offset where the first section that we need to load in is at, and it has the number of the program section headers. That's what the PH number is, right? So if I think there's only 2. This might be a good thing to step through here when we're loading the init process, when we're executing the init process, to check this out. But there's the 2, the code and the text in the data section. So within this here, the 2 kind of important things that happen are the UV malloc is called, the user virtual memory malloc. So this actually creates the page table entries in order to hold the code that we're trying to load, and then we load that segment into those allocated page table entries for the current program struct header. So if we look at UV malloc is going to allocate new page table entries in physical memory to grow a process from the old size to the new size. So it's going to call map pages, which is ultimately going to call, we saw this before, so this is reused both whether we're doing a user or a kernel page space. So this is the thing that walks through there and creates page table entries as needed. So anyway, back to the kexec, after we allocate those, we should actually have valid page table entries in our page table now, set up by this, enough for the size of the segment we're trying to load. And then load segment should cause that segment from the elf file to be loaded then. And this is basically just going to be a byte copy from the file into the memory at the virtual address space where that segment was supposed to be loaded as is specified in the elf header. So yeah, I mean, if you look at these, this is relatively simple, but we've got the open file inode pointers, and we have the virtual address where we're supposed to be reading the bytes out of the open file from that elf header segment, and then just writing them into the process address space at that virtual address. So after we're done loading the segments from the binary file in this ELF format, the stuff right here in kexec is setting up the stack here. So if you look at this closely, this is basically going to malloc 2 more pages at the next boundary. So if I can go back to our figure here, we've loaded text and data segments, and there can be more than one text segment, more than one data segment in an ELF file, but we loaded those in. And then after that, we're going to, we need to keep all these on even page boundaries. So we'll go up to the next page boundary, and then we actually allocate 2 pages, one for the guard page, and then one for the stack we're going to construct here in our process address space. So that's essentially what this user virtual memory malloc is doing. User stack is set to just 1. So, it's something to try out. So if you find that having just 1 page is not big enough for things, you could try increasing this. This looks like they've set this up so that you could have, 2 or 3 pages or however many pages you want for user stacks to increase things a bit. So, but if that's 1, we're actually going to end up mallocing 2 pages, I believe. We've already gone up to a boundary here. And we just zero all those out. And then this loop here is actually copying the arguments onto the stack, okay? So again, going back to this, the result after that loop that we'll go back to is the stack will look like this. So the top of the stack will be at the highest address in memory on the first page, and then the second page is going to be set to be not a valid page, I believe. To act as a guard page. And then we're going to copy in the argv0, argv1, so on strings. We're going to actually copy in the addresses of those arguments, kind of in reverse order, and then the address of the address, or the actual argv pointer that would be passed into main when we start executing the code that we've just loaded here. So here, the uStack is just an array, and so we figure out how many what the argument count is, because remember that argv that needs to be passed into exec has to have a null pointer, right? So if I've only got 2 parameters like I did for here, right? argv0 is pointing to a string constant, argv1 is pointing to a string constant, argv2 is a null pointer. So the argument count is 2 here. Okay. But yeah, we can detect that because this will be a null pointer. This will be 0 once we get to the last argument in our arg count. And that'll end the loop. But for each valid argument in argv, this part here is just copying the string, so copying the bytes out of the argv that was passed in onto the stack. And notice, again, we decrease the stack pointer. So SP is going to be our stack pointer at the top of the stack and lower, so the stack grows towards lower addresses, the way we implement it here for our RISC-V machine. So that's why we're doing minus equals. Minus equals for however many characters we have for each argument, and then actually it has to be byte. It has to be aligned on boundaries. So we also skip over some things if we're not exactly on a 16-byte boundary there. Okay. And then this copy out is what actually does the copy of the character array onto the stack. And I should mention just real briefly copy out and copy in. So there's a little bit of a problem. So the kernel often needs to be able to get things from kernel space into the virtual address space at the right place for a process's virtual address space. So it's kind of what copy in, copy out does. So I won't go through the details of this, but basically, source is going to be an address due to the direct mapping. This will map to an actual physical address of some data that we need that the kernel sees, but the destination virtual address will be a virtual address in the page table that we're trying to copy it into this virtual address space. So this will have the effect of being able to copy stuff as needed, like the initial argument values passed into exec into in this case, into the stack for the process virtual address space that we're creating here. So anyway, that's copy out. That should have the effect of copying each argument value onto the stack. And I think I already mentioned, so ustack is just an array. So, it's just an array of up to max args here. So inside of the loop, we're only putting the argument strings, the argument values on there, but we're remembering the address of each one of those in the ustack. And then at the end, we actually push all of those addresses onto the stack as well. So these are pushing basically the ustack addresses, the address of each arg, the address of arg 0, arg 1, arg 2 onto the ustack. So there we're basically at the end here. So it copies the actual name of the program into the process struct for debugging purposes, but otherwise we're done. So if nothing bad happened, so just to summarize again, we opened up the binary file, read the header first. The header gave us the information for which program segments. Those got loaded here. So, and what was happening here is we're creating a new page table for this new process image. And this is going to be allocating page table entries and then loading each segment into the allocated page table entries. And there can be many text and many data segments that get loaded as part of here. And then after we do this, we construct the stack by hand, which is going to copy the argv strings, the argv character arrays that are passed into the exec system call as the second parameter, this argv array. So those get put onto the setup stack. Remember, the stack actually has, right now, it has just one page to hold stack values, so you couldn't put very much on there, right? So we only have 4,096 bytes that we can push onto the stack before it becomes full, and it will hit the second page. So actually 2 pages get allocated here. I think I skipped over it, but the way that second page becomes a guard page is through this UVM clear here. So that mostly has the effect of it's just finding the page table entry and it's undoing the U bit. So we can no longer access that page if we're in user mode. So it wasn't the V flag, it was the U flag here. I might have said that wrong sometimes, but the effect would be the same. So if we actually do something that tries to read or write on this because we're in user mode and we're doing a function call and trying to push more stuff onto the function call stack, as soon as we get to an address on the guard page, a trap will happen because we don't have the U bit set. It's cleared here. Okay. So anyway, we construct the stack, get the argvs on the stack, and get the pointers to each of the arguments on the stack as well. So, if everything worked, kind of already started talking about these. If everything worked, we're ready to commit. So we can't really throw away that old page table until we know that we successfully created a new page table and are ready to do things. So what happened in order to switch to executing from this new process that we just loaded is we have to have the new page table. So the process that we are execing into gets the new page table we constructed. This is the size of our image now that we kept track of when we were loading all of our stuff on here. So I skipped over this here, but the way that the argv, so the way that the pointer to that array of pointers gets passed to the main function is it's going to be on the A1 register. So the current top of the stack pointer holds the address, basically holds argv that needs to be passed in the main here. Okay, so we put that in there. argc is returned in A0. So we actually return the argument count, the number of arguments that are on the initial stack when we're calling main here. And that's going to end up in argc. From the return from the kexec function. And then the rest of the stuff, the initial program counter, the entry point is in that elf header. So this is a virtual address that should be pointing to one of the text segments that has code in there of the first instruction of main if we're compiling like a C program. So, so by loading this into our trap frame, once we return, once we change from kernel mode to user mode for this process, that will get loaded into the program counter and we'll start executing code at that virtual address that this program counter points to. And then, another register is the stack pointer, so that has to point to the stack pointer for our user stack in the user virtual address space. And then after all that, we know that we were successfully able to load and switch over to the new process page table so we can free up the old one. So, I kind of skipped over, but, go-tos are usually considered bad, but you'll see them used a lot in code, like operating system code, kernel code that's written at this level because it's too complicated otherwise. So basically, if anything goes wrong and we can't finish this off, instead of switching over to the new page table and executing from it like we want to if we're successful, we just free up any uncompleted attempts that we had for the page table, and we return an error code. So if exec returns -1, we know something failed. We didn't correctly execute, load a new program and start executing. Okay, so that's it for this video. So in summary, the points that we talked about in this video. So each process has its own page table, and this is basically constructed when the exec system call is called. So a copy of a new page table is actually created, and the copy is made of the code on the fork. But the exec has the extra stuff in that a completely new page table is created, and the instructions and data for a new process are then loaded into that new virtual address space when we're doing an exec system call. Okay, so we mostly step through the exec system call in this video. It starts basically by creating a new page table. It opens up, so there's two parameters to the exec system call. The name of the file that holds the code in ELF format that needs to be loaded so we can start executing it, and then an argv, so an array of initial argument values that get passed into the main function. And so we start by opening up the binary file. We check if it's in the correct ELF format, and then we load the initial ELF header, which has some indication of the number of text and data segments and the virtual address where each segment is supposed to be loaded into the process's virtual address space, among other information, and the entry point. So the first instruction within that virtual address space that we should start executing from. So I think there's other segment types, but in this class we'll mostly see text and data segment types. The text, may seem like a strange name. So for historical reasons, these are called text. These are really holding instructions. So these will be segments that will be flagged in the ELF header as read and execute, but not writable. So we don't want to be able to actually have self-modifying code. And so when we're loading these in from the exec system call, we're going to set the U flag in the process table entry for each one of these segments that's in a text segment, because we only want those pages to be, we want these pages to be able to be executed when we're running in user mode. And likewise, if we have a data segment that we're loading from an ELF header, these get loaded by kind of calling those functions in the vm.c that create page table entries as needed and fill it out, and then basically load the stream of bytes from the file into the virtual memory address space that was set up for those. So data segments are going to get loaded as read writable but not executable. Also, the U needs to be set for all of these so that the normal user process can access these. So when that happens, then after we're done with that, a stack is actually created. By default, right now for XV6, it actually allocates 2 pages. One is going to hold the stack, so enough room for 4096 bytes on a function control call stack, and then a guard page that has the U bit not set, so that if we try and do any access on the guard page by overflowing the stack, a trap will happen, and we'll know that we overflowed our stack. And the initial arg values and pointers to those are actually copied onto the stack pointer. And then at the end, if everything's successful, that new page table is put into the process table entry for that process. And then the program counter and the stack pointer are set in the trap frame so that on return from kernel mode to user mode for this process, it starts executing. So the program counter is going to be set to the entry point that's indicated in the ELF header. And then so on return to user mode, that program counter is what will be loaded, that virtual address of the entry point, and we'll start executing basically from the main function if we compiled like a main program that we're doing here. Okay, so that's it for this video. So there was a lot in there, but this is important stuff to make certain you understand. As usual, if you have questions or things, let me know. But otherwise, I hope to see you in class, or hope to see you in our next video.